the last lecture for the session is Bryna Kra, who said about system with low complexity.
So thank you very much, and I'd like to thank the organizers, also add my thanks to this terrific meeting. It's nice to be back here. I have to start with an apology to Hillel. I will not be talking about things that I learned here and things that I worked on, inspired by many of the people in the audience. But in spite of that, the things I will talk about really were inspired by what I learned here, in the sense of this combination of structure and algebra and analysis and dynamics together, and looking for structures in dynamics. And so there will be no non-conventional multiple averages in this, but something else. So first, everything I'm talking about is joint work with Van Seer. So all of the theorems that I will say are joint with him, even if I neglect to mention that again. So let me give you the setting. So my setting, I have to make a second apology. I might not get to measures. I will try, but there will be some measures in the end if I get there, but I may or may not get there. So for now, I have continuous setting, topological. This is a shift system. So sigma will denote the left shift, and x is closed and invariant with some finite alphabet, which I will denote as A. And these are z shifts, and so my alphabet is finite. Okay, so sigma. And what I'm going to be talking about is automorphisms of the shift system. So what is an automorphism? An automorphism is a homeomorphism phi from x to x that commutes with the shift. Okay, so I will cover this up for now. Is it on this one? No. Oh, yes. Okay. So in particular, you notice immediately that the shift itself and the subgroup generated by the shift is in the center of the automorphism. Good. Center of automorphism. And I will denote by aught of x. I really should denote it by aught of x and sigma, but I will typically just write this as aught of x for the group of automorphisms. Okay. So there's an old theorem of Curtis, Hedlund, and Linden that's classical. It's in a paper of Hedlund, which says that the automorphisms are all block codes. So in particular, I won't write it down or even explain, but it just means that every automorphism, if you want to know the entry over there, it's determined by some finite window that you need to look at, and it'll tell you what to do. But as a corollary of this is just that the automorphism group is countable. Okay? But it can be huge, and lots of times it is. For example, if it's the full shift, also in the same paper of Hedlund, he proves that the automorphism group contains lots of structures. For example, it contains isomorphic odd x, contains isomorphic copies of, I won't write isomorphic copies of, but it contains every finite group. It contains the free group on any number of generators, finitely many generators. It contains every countable locally finite group, residually finite group, lots of other things. Fundamental group of a surface. There are many other things that are proven in this paper. Direct sum of countably many copies of Z. So more. And this was extended in the 80s in a paper of Boyle, Lind, and Rudolph, that the same kinds of structures always occur in a mixing shift of finite type. So the automorphism group has lots of structures, so for mixing SFTs. So what's going on here is that there are very, very few constraints on what it means to be an X, a point X in the space X here. And so there are lots of automorphisms around. that can do this, subject to the constraint that it has to be countable. Okay, so in particular, all of this is the world of positive entropy. Okay, all of these kinds of things. And so I want to, the main question I want to give you a picture of what's known and what's not known is what happens for the automorphism group of zero entropies. Shifts. Okay, so okay, so as you would expect, there should be fewer automorphisms, but the question is how few and what kind of structure. So let me give a definition of the complexity. So px of n, it depends on x, the system x, but I will typically write this just as p of n and omit the system that will be fixed in advance. This is the number of words. So this is the number of words of length n. Okay, so meaning I look over all the supremum over all. I take windows of size n, and I look over all x's in my space x, and I look at how many different words I can do, counting that. So the exponential growth rate of this is the entropy, but I'm interested in things that do not grow exponentially. Okay, so it's a function, Pn from the natural numbers. To natural numbers, and there's some very trivial facts that I'll just write down just to p of 1 should be the size of my alphabet, otherwise I may as well throw out things from my alphabet and not include them. And it's a non-decreasing function. P of n is less than or equal to p of n plus 1 for all n. And these two facts are enough to conclude the Morse-Hedlund theorem, which says that there exists an n such that p of n is less than or equal to n if and only if the system that's generated by this is periodic, if and only if the whole system is periodic. I'll write this as there exists n in n such that p of n is less than or equal to n if and only if x is periodic. So the proof of this is pretty quick. Periodic obviously implies that there's some window in which you see no more. And if I have this, you combine it with the fact that p of 1 is greater than or equal to 2, otherwise it's trivial. P of n is less than or equal to n plus 1. When I have this, that means that there's some place where it stabilizes. P of j is equal to p of j plus 1. So what does that mean? If you look at a window of size j, there's only a unique way to complete it to a window of size j plus 1. Okay? Well, there's finitely many windows of size j. One of them repeats. Now you have a period that comes up. I won't write the details of that, but this is not Morse and Hedlund's original proof, but it's immediate from these facts. So what does this mean, at least in terms of the automorphism group? It means that if you have this type of complexity at some bound p of n less than or equal to...
Periodic means just...
periodic here...
There's not just one orbit.
I'm not assuming there's one orbit. I'm just assuming there's something which I can copy. Yeah, that's right. So every element in the shift is periodic. Yes. Okay, so in this setting, at least in the Morse-Hedlund complexity assumption, the point is exactly what you've just said, that the automorphism group is finite. Okay? Okay, so what I really, and more generally, in fact, if I have p of n over n tending to 0 as n goes to infinity, then also the automorphism group is finite. You can, that follows as a corollary. So the more interesting case is going to be when my growth is at least linear, and I'm interested up to sub-exponential growth of the function p of n. Another way that I want to think of this result is that z embeds in the automorphism group if and only if my complexity is unbounded. Okay, so that's how I would like to view this. Okay. Okay, so the cases that I'm interested in is when we have some bound on the complexity. Well, I need at least that this in the limit And of course, there's different choices of what kind of limit. I could take a lim sup, or I could consider a lim inf as n goes to infinity. I'm not assuming both. I'm assuming one of them at different times. It should be positive. Up to, I would like to consider things up to when this growth, when I look at divided by, well, let me do this, log. So sub-exponential growth will be log of the complexity divided by n to the beta is 0 for some beta. And again, I could ask for for lim in, for lim sup, and there may be different results for that. Okay, so the first case, I'm going to start at the top, highest complexity, with beta bigger than or equal to half, and here there could be a lim sup or a lim inf, is my assumption. That's my first open question. I have nothing to say about that. Okay, so that's the end of that story. Okay, how about beta less than a half? I don't.
Do there exist such things?
Do there exist such things? Yes, in fact. You can construct such things with this growth. Toplets-like systems can be used to give whatever complexity growth you want. No. 0 less than or equal to beta less than 1. But what I can't do is anything in that range. I have no story to tell. And that's the end of my story for that. Okay, so let me go to the first. Yeah, I think I'm going to put it over here. So as you would expect, of course, the lower my complexity goes, the more structure I should find. But the question is really how much structure? And where does the dividing line between different structures happen? I would point out that in positive entropy, when we're talking about showing that there exist all sorts of structures inside there, you can also have positive entropy with a very small automorphism group. You can make it Z. So it's not something that you would want to hope. But the question is, on the 0 entropy, can you restrict the automorphism group to throw out all of these structures? So it's the opposite question. So starting at the top, being in the high entropy, I'm going to assume further that this is a minimal system, meaning that the orbit closure of any point in the system is everything. Okay? And so here I'm assuming, assume there exists some beta between 0 and less than a half, such that it has this growth rate, and this is with a lim sup. So log of the complexity over n to the beta is 0. Okay, well then the first thing is, which I should have pointed out is very not true for the full shift or mixing shifts of finite type. The first thing that happens here is that the automorphism group is amenable. Okay, so this is already in sharp contrast to what happens for positive entropy situation. And furthermore, we can say something more about this. It's not just amenable, but it has sub-exponential growth. And then let me make that precise, because it's in terms of any finitely generated, torsion-free subgroup of the automorphism group then has sub-exponential growth. So there's different sorts of notions of size going on here. This is the growth rate in terms of the complexity. Sub-exponential is what comes out of this. So in particular, when it's sub-exponential, it implies that it's amenable. But this is a stronger statement that it's actually sub-exponential growth. So here, the growth is in terms of the word metric on the group. So if you, what I mean by this is if gamma n denotes the growth of the counts the number of distinct group elements that can be written as a product of some generators, symmetric set of generators, then, well, gamma n depends on the choice of generators, but the growth rate of gamma does not. And it's in this sense that the growth of gamma, which is sub-exponential. Okay, so. No, it depends. It definitely depends on beta. And it depends on which subgroup you would pick. If you pick a different finitely generated subgroup, there's a growth rate, but they could grow slower. I mean, it's not.
But you can go arbitrarily close to exponential growth, or you cannot?
I don't know. I do have an actual bound on the growth rate, but I have to look up exactly what it is.
Depends on beta.
Which it depends on beta, definitely. Yes. 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 I have a bound, but I don't remember what I didn't write it down.
What about distortion theory?
Yeah, I don't know how to get rid of it. I don't know. There are some cases in which we can, but when we only have a lim sup assumption, or when we have a lim sup assumption without something stronger than that actual limits, I don't know how to get rid of the torsion free. I don't know that there is torsion, or can be such examples. So, okay, but is it clear what I mean by this? That if you take the log of this, divide by n, you take the limit, this goes to 0 for the growth rate. Okay. So I will say a few words about the proof in this in a minute, but let me state this is the first part, and this second part is what happens when we drop further down to polynomial growth. Okay, so with polynomial growth there's even more structure. Again, I'm still assuming minimal. But now I'm just assuming that there exists some d. So I'm going to erase this. D such that, and again, it's a lim sup assumption. There are some times when we can weaken this to get a lim inf. But p of n over n to the d, this is equal to 0. Okay? So in this case, it turns out, well, we already have that the automorphism group is amenable from the first statement. But here we can say more. And this is, again, about finitely generated. Torsion-free subgroup of the automorphism group. So here it's virtually nilpotent. And in fact, there's a dependence of the degree of nilpotency on the D here. And the step of the nilpotence is less than or equal to -1 plus the square root of, well, I'll explain where this comes from in a minute, 8d minus 7 over 2, the greatest integer in this. So there's a sharp bound on the step. So it's virtually nilpotent, and I mean the step of the nilpotence, how far up in the nilpotent chain, the central series. Yes. And I use Bas-Givarsh to get this, yeah. There's no beta in here. This is growth rate, a polynomial growth rate, so it's n to the d. So it depends on d strongly, although that's an open question if it really does depend on d or not. Okay, so here, the bound that I've given you, it's at most this step. I don't know. It might be smaller. Okay, so in particular, but the way I want to think of this is in a similar way to how I thought about the Morse-Hedlund theorem. What it says, this says if your growth rate is little o of n to the d, then zd does not embed. And that's a corollary. And in particular, this bound says that if your growth rate is little o of n cubed, then you're virtually abelian. Okay? Well, every finitely generated torsion-free subgroup is virtually abelian. Nope, that's question number 2. Okay, so okay, so if p of n, let's say, is little o of n cubed, then finitely generated torsion-free subgroups of the automorphism group are virtually abelian But I don't know if that is really the right conclusion for this theorem. Okay? We only have a bound on the step. So that's so question, an open question is, does the same conclusion for D bigger than 5? The reason I say D bigger than 5 is because Fabienne Durand has told me, and Samuel Petit told me they have an argument for improving this to little o of n to the fourth, and you still get virtually abelian out of this. Okay, so maybe D bigger than 5 would be the place to start looking. And the only thing one has to do is get rid of the Heisenberg group. If you can show that the Heisenberg group does not embed, then you would be virtually abelian. So I'm getting rid of one of my favorite objects, but okay. So let me say a little bit about the methods here. First of all, let me take a moment and ask if there's any questions on the statement of these theorems. And then we'll go into stronger statements that can be made, but these are at least what we know in this generality. Okay, so for both of these, what we do is to show that it's amenable is we explicitly construct a Fulner sequence. Okay, now there's I think I will leave the theorem up. So in order to construct the Fulner sequence, we use words. There are special words, so words in the alphabet, that for at least some amount of time, depending on the growth rate, whether it be the stretched exponential case of n to the beta or the polynomial, there are words that can be extended uniquely. And the question is how big these words can be and how much. So, for example, in the first case, we use words of length n. You show that there have to exist words of length n that can be extended, much like the short argument I gave you for the Morse-Heitland theorem, that if you have a window, when it stabilizes the growth rate and it extends uniquely, well, here there are words that are of length n that can be extended at least, well, in the stretched exponential case, it's n to the 1 minus beta entries to either side. And we need to find large words that do this and use those words to construct Fulner sequence to cover all of the range R automorphisms. And so if the complexity grows sufficiently slowly, i.e. not exponential growth of this, then there are words that do this for a long enough period. And so that's the input. Correct.
You mean Windows.
This I mean windows. I don't mean words, correct, I don't mean words in the automorphism group here. We're going to use these type of words that are in the shift to build automorphisms of range R to then control the ball inside the word metric, the growth in the ball. Yeah, that's why I said it's a little confusing because there are two different notions of growth at all times. So then once we get these words, we explicitly construct Fulner sequences. To cover the automorphisms of range R, and there's a dependency of the R on the N and the beta, but I will omit all of the dependencies. And this is exactly where so this would be enough to give amenable, but we need to control the growth of this in order to get the sub-exponential growth in here to get the stronger statement. So we have to control how these grow and the growth rate of the R's in terms of all of the parameters. And this is exactly where the restriction on beta comes in, that beta needs to be less than 1/2, because we end up with, we need to look at words that are at least length n to the 1 minus beta to do this. And then from the growth rate, there's beta of them, so you get n to the beta minus 1 over beta, and this is what we need to be less than 1. Everything goes through. For beta bigger than a half, it just doesn't say anything. So it just doesn't, we can't conclude anything because we need this.
Beta is very, very small, very close Are you going to get that the sub-exponential is what?
Yes,
Is what? It's also going towards zero?
towards zero. The sub-exponential, the growth rate will be, so if beta is very small, this is small, yes. So it grows like this in the ball.
This is the dramatic achievement.
We don't know that, it could be much smaller. It could be much smaller. We're not claiming that we have an example, which would do some beautiful things, I agree. Yeah, but we don't know. So all of these theorems, these should be phrased as has sub-exponential growth, at most sub-exponential growth. And these theorems should be, it's virtually nilpotent at most this degree. I don't know. I don't have real examples. No. There's a real lack of, I have some examples, but they don't answer any of the questions I'd really like them to answer, unfortunately. Okay. And for polynomial growth, what happens? Well, you start with the same scheme of building the Fulner, constructing a Fulner set. And then what do you end up with? You end up with that the growth rate here, I have log gamma n over n to the d. In fact, I end up on a subsequence, lim inf as n goes to infinity, is 0. So this is Gromov's theorem. Well, it's a Gromov's theorem on subsequences, which is Van Dries and Wilke's version of Gromov, improved slight generalization of Gromov's theorem, which then gives us that it's virtually nilpotent. And because I know the growth of this, then I can apply the Bas-Guivarch formula to get exactly this bound out on the nilpotency. Okay, so this is what's happening in the polynomial case. All right. So it's an outline of the proof. But now I want to say what happens when we drop further, because when we get lower in the complexity, we can say even more. So, what's lower than polynomial? Well, in all of these, there was a lim sup assumption. And all of these, there were two places here that I'm stronger than I might want to be. One was that I'm always assuming a lim sup, and the other is that I was always assuming minimality of the shift. Okay, so I'd like to look at more general. And so if we assume just transitivity, so meaning the existence of a dense orbit rather than all orbits dense, and this is now a lim inf assumption here, so I can weaken the assumption here, but it's only going to be true for sub-quadratic. Okay, so now it's in the lower end. I mean, these theorems still apply, but here we get a stronger statement. So you know that the automorphism group always has the shift in it, so the group generated by the shift. But here then the automorphism group is periodic. So it's a periodic group, meaning every element has finite order. The method for this, well, the assumption is different. It's a weaker assumption. And the method for this is quite different than those methods with the estimates. And this involves, by the method of this, well, I'll very briefly just take 1 minute to give a sketch. You think of the shift as being a coloring, and you use an automorphism to construct. So this is the shift, the original. It's transitive, so I put down the transitive, a transitive point there, and it's coloring. And the shift is acting here. And now I put down an automorphism and make the coloring in Z2 that results. So this continues. And then the complexity assumption, the subquadratic complexity assumption here, gives me some large rectangular windows on which I can control the complexity. And in fact, I can control these windows in terms of the area of the windows. And you get that if this is an n by k window, one can show that there exists n and k such that the complexity of this n by k, a two-dimensional version of the complexity, is bounded by, let's say, nk over 100 or something like that, nk over some large number. And then there's a theorem of Poisson-Zamboni, which says that there must be a periodic direction in this configuration, and the periodic direction comes from a given finite list of choices that depend only on the configuration. And then one goes back and uses this information back in the shift to show that you get only periodic elements. So it's a completely different method of proof than this one. It involves passing to a Z2 picture to understand what's going on. So that's sub-quadratic. And then, well, you could ask, well, is anything stronger than linear? By the way, I'm not telling you these things in historical order. In fact, this was the first theorem we proved. The next theorem is the one I'm about to tell you, and this is the one we have just proven recently. So in the linear case is the only one where we really understand all of the behavior. So in the linear, well, there's a couple of different, so almost all of the behavior. First, let me say something. So far, we've always had a dynamical assumption, but now let me say something about any shift, so no transitivity. And the complexity assumption here will be the lim sup, and it's a lim sup assumption that it's bounded, so less than Pn over n, so it's linear growth. Let's say it's less than k. Then in this general setting, we get a similar statement to the ones that we have in the higher complexity. You get that every finitely generated subgroup, there's no torsion here, but every finitely generated subgroup of the automorphism group of X is virtually ZD, where D is, for some D, I put less than, okay, so for some D less than K. Okay, so here we have a lot of structure, and in fact, this one you can achieve, unlike the previous ones. There exist examples that this happens with this complexity. If you have the same complexity and you have the existence of a periodic set of points, then you can get rid of the virtually part, and it's actually just, sorry, you can get rid of the finitely generated part and say you're just actually, the whole automorphism group is virtually ZD. If you have the same complexity, but now I add in transitivity, well, by what I just said, you can again get rid of this, but you get a stronger statement. You get here that the automorphism that gets rid of the finitely generated part, but here the automorphism group, if it's transitive, is just virtually Z. It goes all the way down. And there exist examples again. And if you have minimal, and now you can weaken this to a lim-inf assumption. So the difference here is not just minimality, but you weaken the complexity assumption. Then the automorphism group, the size of the automorphism group, well, I have to mod out, of course, by the shift, which is in there. But if you do this, then this is less than K. Okay, and this result has been proven independently by Donazeau, Durand, Mas, and Petit in a paper which was right at the same time as we did this one. Okay. So there's lots of things that live in this regime of linear growth, the Sturmian things, morphic shifts, interval exchange transformations, and I think I will have a few minutes to say something about that, codings of interval exchanges.
Do you have any example of transitive but not minimal?
You mean so? You mean to no? No. So I don't know if there really is any difference between these two things. Yeah, I don't think so either, but okay, I don't. So the methods for this are, again, a different set of methods than the previous ones. They really are very linear in the methods. They use very strongly the fact that the complexity, when the complexity is linear, this is if and only if the first difference is bounded. You know, so if you look at Pn plus 1 minus Pn, that this is bounded. And this appears various places in the literature. A statement like this in Cassin was where we learned this lemma that we use. But I guess what I want to emphasize, just say about this, is that they're strongly linear techniques in this picture. And, well, that bound that's there is used for up to here, for the general case and for the transitive case. What we do is, using this kind of that the difference is bounded, in a transitive system, well, first we deal with this dense set of, if you have a dense set of aperiodic points, we deal with that case, you break up the orbits into pieces. Because of the complexity assumption, you can't have too many orbits. You have a bound on the number of different orbits that can be there, and you work in each orbit to get this kind of a result. So for transitive systems, then an automorphism is determined by the image of the transitive point, and you're basically finished, almost finished at that point. The set of images is then contained in finitely many distinct orbits, and that gives you virtually Z. For minimal, though, the proof is different, and our proof was based on the lemma of Michael Boschernitsen. So I think I will take a little bit of time to tell you about that in a moment, of where that came from, but maybe I will, before that, just give a quick summary. Just to make it clear what's going on here, is there are various different things you can play with here. Of starting with the dynamic or growth assumption, what type it is. So for example, positive entropy. Here you could be mixing SFT, for example, as the dynamical assumption. And the automorphism then group is, well, I'll just say it's big. Okay, there's lots in there. You have lots of different things. When you go to the growth rate, so log p of n over n to the beta, well, there's two different things that happen. You can do beta bigger than a half, and I don't know anything, and beta between 0 and a half. And then we have these results that say that you're amenable, the automorphism group. The dynamical assumption here is minimal. And here you get amenable plus the fact that you grow sub-exponentially. There are examples that grow this way, but their automorphism groups, all the ones I know, their automorphism groups are much smaller. They're virtually Z, in fact, which is a little bit of a sad case. I don't even have a nice example over here of a non-abelian automorphism group in this setting, so beta less than a half. I don't know what happens if you reduce this. This was a lim sup assumption, and I don't know what happens if you reduce it to a lim in. If you now go down to polynomial, so p of n over n to the d for some d, this goes to 0, and this is again a lim sup. Again, there was a minimal assumption, which we don't know how to lift. Now you get better than amenable. You get every finitely generated torsion-free subgroup is virtually nilpotent with a bound. But as far as examples, once again, all the examples we have are actually virtually Z. Okay, so. And then in the lower cases, we have a much better understanding of the quadratic, the sub-quadratic, and the minimal, and the linear. And so sub-quadratic, we're able to lift it to transitive, and here we're able to say something about any kind of dynamical assumption that you want. Okay? So that's sort of a picture of how things live. And let me just take the last few minutes, I think I still have a little time, to tell you about the idea that came into this and another question that it inspired. So I will get to measures at least. So. So this idea that I told you before about words, and these are words in the shift language that are uniquely extendable, well, this comes up in some way in all of the proofs, that you have to look at these words that play the special role of being extendable. And there was a finitary version in a paper of Michael's from the 80s of such a notion. So what he used this to prove, I won't state the lemma, but the theorem that he used this to prove was that if you take a minimal shift and you have a linear complexity, and his was slightly weaker assumption, but I'll just, to be consistent with what I have been writing up till now, I'll write it this way. So if this is linear, so there exists some k such that this is bounded by k, then he showed then there are at most k minus 1 ergodic measures. So this is really a linear statement. I mean, as soon as you go beyond linear, you're not going to get a bound on the number of measures. But in the case of linear growth, it gives you a strong bound on the number of ergodic measures. As an application, you get, well, a worse bound than the best bounds for interval exchange transformations. But if you apply this to the coding of an interval exchange transformation, it would immediately give you that you get at most k minus 1 ergodic measures. So this is not as strong as the Katok-Veach bound of k over 2, or the greatest integer in k over 2, but it's a much easier proof in some ways. Or at least to me, it's a much more intuitive way to go about. It doesn't give the strongest bound, though. And so in this paper, he asked, can this bound be lowered? And and we asked several other questions. Do you need minimality? And are there other measures that you can do this for? So in what ways can this be improved? And so let me just give you a definition. If I have a compact metric space, so now I'm no longer just compact metric space, then what does it mean for a point to be generic? Well, we've heard this many times here, but so mu is Borel, probability measure on this metric space. So I guess I need a transformation, measure preserving transformation. Then X is generic if it has good statistics, if the average is, so generic for this measure, generic. For mu, if when you take any continuous map, if for all f continuous, you get the right statistics. Okay, so the limit as n goes to infinity, the averages of the ergodic averages. Integral of f du mu. Okay, so for an ergodic measure, oh, sorry, I didn't define what does it mean for the measure to be generic, and we say that mu is generic if there exists a generic x for mu. Okay, so for an ergodic measure, almost every point is generic, but there exist generic measures that are not ergodic. And so the theorem that we prove, I think I'd like to leave that up, so I'm going to, having just written a definition, I'm sorry to erase it, but well, I'll leave up the complexity assumption, and I'll leave up the conclusion. This is, again, all joint work with Van. So if I take a shift system, and I have, again, the same linear complexity, then they're at most k minus 1. They're at most k minus 1 generic, non-atomic measures. Okay. So first of all, there's no assumption of minimality here. I erased that assumption. And it's a bigger class of measures. And the reason that we became interested in this, after using this lemma for other purposes, there was a recent paper, well, yeah, maybe I'll say that in a minute. So there was a paper of Chaika and Maser, or let me back up for 1 minute before that, is in particular, if you look at the coding of an interval exchange transformation, which I won't define, I'm assuming everybody knows what an interval exchange transformation, then you have at most, the coding has order, so it gives you k minus 1 here, and so you get at most k minus 2 generic measures on an interval exchange transformation. So that's a corollary. Interval exchange transformation with k intervals has at most k minus 2. That comes out from the symbolic coding of it. You get the more minus 1 generic measures. And this was an answer to a question that was posed in a paper of Chaika and Maser. And what they did in their paper is they constructed a 6 IET. It's not uniquely ergodic so it has 2 it has exactly 2 ergodic measures, so exactly, it doesn't have more than 2 ergodic measures, 2 ergodic measures, and 1 generic non-ergodic measure. Okay? And they show there is one. They don't show that there's not more than one. They just show that there is a generic non-ergodic measure. And they asked in this paper, first of all, is there a bound in general for an IET on the number of generic measures? And so this was an answer to that question. But unfortunately, it doesn't tell us that the bound is sharp, because if they put another generic measure in there, we would be sharp for the bound. But I don't believe there is one. But their example is tricky, and neither they nor we have been able to check if there could be another generic measure in there. So I don't know if for interval exchange transformations, which is obviously a much smaller class than this, if this theorem is sharp, but we do have an example to show that this is sharp. Meaning, so this is also the answer to Michael's question from his paper. So there exists, if you give me any D, there exists a minimal system, a minimal shift, that has exactly D ergodic measures and all the right complexity with, and this is a construction, exactly D ergodic measures. No, it also has no non-ergodic generic measures. And moreover, the complexity, obviously I need to tell you what the complexity of this guy is, but the limit growth of the complexity P of n over n is exactly this number of measures, D, and the lim sup is one more. So it's sharp in all of these senses. The lim sup of the P of n over n is D plus 1. Okay, so this example, which it involves in fact, the example is much more work than the theorem. So the theorem, let me just say a couple of words, since I think I'm basically out of time. So we have to really carefully estimate what happens to the complexity when we have different generic measures. So too many generic measures sitting in there, by looking on big windows and seeing what happens, estimating along orbits using similar ideas that we used in the linear complexity paper to do that. But the construction is sort of a little bit like inserting spacers into a Toeplitz type construction to get lots of self-similarity in here to control the complexity and build in different ergodic measures that live on there. Okay, so with that, thank you very much.
What do you learn about specific
So Sturmian is completely understood that you just get the shift plus a involution. I assume that this was known a long time ago, but the only place in the literature I found it is in a paper of Ali from 2014. It's a very recent paper. So substitutions for very specific ones, there are in this paper of Sebastian and the one that I cited before. They have a lot of examples, computations of these things, but there's a lot that we don't know.
Two questions. So one is, do you know what complexity will guarantee that the shift is the center?
No. So a version of Ryan's theorem, you want that the shift to actually be the whole center. No.
Okay.
No.
And the other natural question is, now that you know that in these cases the automorphism is amenable, you have automorphism invariant measures. So you have a bound on those, and hopefully just one.
No, this was last week, so no.
Asking it.
So I don't know if anyone's done beta shifts. Did you guys do beta shifts? No? No, I don't know.
And you can construct automorphisms for any rate of n.
Yes. That is true. You can use a Toeplitz type construction to get whatever.
And this is exhaustive of all examples of automorphisms.
Well, they don't give you these answers It's not a tuplet strictly, but you can spread things out and control.
Shift, huh?
Right. Well, I want the automorphism group of the shift, but not the actual. But no, I don't. I mean, I can get the complexities. You can construct any of these complexities. That's not hard.
I think assignment is a specialist.
Yes.
There are asymptotic complexity close to some function.
That is correct.
It's a suppose.
So for measure theoretic complexity, no. There are some results controlling the automorphism groups that were done in the 80s. There are results of Host and Perot and others, but I don't think there's as complete a picture.
Very foolish question. Can you
Then I have a chance to answer it.
a single automorphism of finite order, a non-trivial automorphism, finite order?
So you can. I mean, you can construct these. But the ones that we get out when we do this, we end up with shifts that are very non-minimal. So if you allow me to take off the minimality, then we can do things like that. In fact, I can make over here, even in the quadratic, as close to quadratic as you want, something, it's not transitive at all, but something which has an automorphism group that has all sorts of properties that you want. I mean, I can make it grow. It doesn't have sub-exponential growth, and it has lots of periodic points. But
You can say